FM5 3 Hypothesis Testing Part 1. This video we need to understand and use tests for specified mean of any distribution whose variance is estimated from a large sample by using the central limit theorem, the difference of two means from independent normal distributions with known variance, and specified mean of a normal distribution with unknown variance. The central limit theorem states that the mean of a large sample from any distribution with known mean and variance has a distribution that is approximately normal. And if we are using a Poisson distribution, which has got mean and variance equal to lambda, then for large lambda we would use the normal distribution and we would have to use a continuity correction going from a discrete distribution to a continuous distribution. Then for a binomial, which has got parameters n and p, for large n we would use normal distribution with mean np and variance npq. P has got to be between 0.1 and 0.9. If p is smaller than 0.1 or larger than 0.9, we would use the Poisson approximation to the binomial. For a continuity correction, being as these two are discrete distributions, if we wanted the probability that x was equal to some value k, then we would need to go either side of the k 0.5 so that we would make sure that our k was included in our interval. If we wanted the probability that x was less than or equal to k, then we needed to add a 0.5 to make sure that the k was included, and if we wanted to be the probability of x greater than k, then we need to take a 0.5 from k to make sure that our k is included. In case we're given a PDF, the expected value of a PDF is x times f of x, integral of that, and its variance is e of x squared minus e of x all squared, where e of x squared is the integral of x squared times the function of x. If we wanted an unbiased estimate of proportion, that would be x over n, x being the number of successes over the number of trials, giving us our p. So the expected value of the proportion is our little p, and the variance is pq over n for this situation. An unbiased estimator for sigma squared is s squared. So when we don't know sigma and we need to estimate it, we use s squared, where we divide by n minus 1. So sum of x squared minus sum of x all squared over n, all divided by n minus 1. And a reminder that the sigma squared, originally we divide by n. So n times sigma squared is equal to n minus 1 times s squared. If we've got a normal distribution and the sample is small and the population variance is unknown, we have to estimate the population variance. We must use the t distribution tables, table 7. We'll come across a few examples of those later on. For a sampling of a mean from a normal distribution, the mean is also normally distributed with mean mu but variance sigma squared over n for a sample. So the standard error is the standard deviation of the sample mean, so we take the square root of the variance. If we are comparing the difference between two means, then x bar 1 minus x bar 2 would also be normally distributed, with their expected value being the difference of their means and their variance being the sum of the variances of the two separate distributions. Divide by n because we're talking about sample means. For testing hypotheses, we need a null hypothesis that is equal to a given value, the parameter is equal to a given value, against an alternative hypothesis, H1, where we are checking if we are less than, greater than, or not equal to a given value of H0. If the alternative hypothesis is greater than or less than, then this is called one-sided. But if it's not equal to, then this is two-sided, and we have to double the probability. So if we're greater than theta, say, then our p-value is the end bit of the probability. If we are less than, we have the p-value being the least tail of the probability. If we are two-sided, we need both of them. If it's not equal to, then we need to double our probability. The p-value is the probability that the observed result, or a more extreme one, will occur under the null hypothesis. And a p-value should be along the following lines. If it's less than 1%, there is very strong evidence for rejecting H0. So we're far enough away from H0 that it does make a difference. If we're between 1% and 5%, there is strong evidence for rejecting H0. But if we're greater than 5%, then there is insufficient evidence to say that H0 was wrong. Sometimes the question gives you the value where you keep or discard H0. This is called the significance level. And we have a critical value for theta where we accept or reject H0, and a critical region would be the set of values within the area that we reject H0. So we've got a significance level in some questions, or they say use discretion, so you'd use your 1% and 5% from the last slide. Question 2006, 5b. On any weekday, the number of passengers X using an early morning bus service may be assumed to follow a Poisson distribution. In the past, the mean value of X has been 2.4. The local council wishes to increase this mean, so they decide to offer this service free of charge. Clearly stating your hypothesis, during the 100 weekdays following this offer, a total of 280 passengers use this service. Determine at the 1% significance level whether or not the offer has resulted in an increase in the mean number of passengers using this early morning bus service. So we've got a Poisson distribution and we've got 100 weekdays. So we're going into the normal distribution. So our hypothesis is that lambda stays as 2.4 against that lambda has increased from 2.4. So on any one day, our X is distributed in Poisson distribution with a 2.4 mean. But in 100 days, our mean increases to 240. Therefore, we are going to use a normal approximation where our mean and our variance are both 240. So we're now using normal distribution, but it's a discrete distribution, so we're going to have to use continuity correction. So our p-value is the 280 in increased enough for them to say that the mean has increased significantly. So we are using the continuity correction, so I need to keep the 280 in, so I need to go to 279.5. I change that into Z. So 279.5 minus the mean we are trying to test, divided by the square root of the variance, and we get that Z, the probability that Z is greater than 2.55. So looking at table 3 and using 1% significant level, so we are looking for Z greater than 2.55. So there's 2.55, but that's up to 2.55, so we need to take that away from 1, and we get a p-value of 0.00539, which is less than 1%. Therefore, there is very strong evidence to reject H0. So at a 1% significant level, we say that the mean has risen. So that was using normal distribution for a large value of lambda. Another question, 2010 2b again, slightly different from the last one. The number of computer breakdowns per day at a large office may be assumed to follow Poisson distribution with mean mu. The IT manager believes that the value of mu should be 1.5, but he decides to check this. He therefore defines the following hypothesis. So mu is equal to 1.5 against mu is not equal to 1.5. So it's a two-sided test. For this test, he decides to count the number of breakdowns occurring during a 100-day period, and given that 170 breakdowns occur, calculate the approximate p-value and state your conclusions. So we're not given a significance level, we have to decide on the outcome. So therefore, it's two-sided, mu equal to 1.5 against mu not equal to 1.5. In 100 days, our Poisson has increased, the mean has increased to 150. So now we go to normal approximation, where our mean and our variance is 150. Our p-value twice that the sample, 170 breakdowns, is significantly different from our mean. So greater than or equal to 170. We need the continuity correction, being as we're talking about a discrete distribution going to a continuous distribution, so we need to take 0.5 before the 170. Change that into Z, so 169.5, take away the mean, divided by the square root of the variance, and we get that we want twice the probability that Z is greater than 1.59. Table 3, and we get 1.59 being 0.94408. So I want 1, take away that, being as I want above 1.59, and double that, being as it's two-sided. We're now above 11%, therefore not enough evidence to reject H0. The mean is still 1.5 breakdowns a day. Another question. A dairy sells butter in large packs. The owner states that the mean weight of these packs is 1.5 kilograms. Quality control check, 80 packs are chosen at random and the weight X kilograms of each pack is measured. The results are summarized below. State a suitable hypothesis to carry out a two-sided test and calculate the p-value of these results and state your conclusions. Then two different approximations that you have to make in your analysis. And therefore, our hypothesis is that the mean weight of the packs is 1.5 against it's not equal to 1.5. Wanted a two-tailed test. Okay, so the expected value of x bar is the expected value of the sample, which gives us a mean of 1.515. So from the sample we get that. Our variance, we need to estimate the variance. So we're using our S for an estimate of the variance. So 1 over n minus 1, 79, sum of x squared minus the sum of x all squared over n, and that comes to 0.010152. So our variance for the sample mean is the variance of x over n. Our estimate for the variance of x is s squared. So that divided by 80 is our variance for x bar. So now then we need p-value. It's two-sided. So our sample gives us a mean of 1.515. We need to know, is that different enough from 1.5 to say that we're significantly different, that we have made a difference. So twice change that into z. So take away the mean of the what we want to test, divided by the square root of the variance of the sample, and we get the z is greater than 1.332. We want twice that probability. And looking that up in the tables, taking it away from 1, being as we wanted more, and doubling it, and we get 0.1835, which is not less than 5%. It's greater than 10% even. So we keep H naught, there's no change in the mean. So the mean is 1.5 kilograms. Now what approximations have you used? So we have used a large sample, therefore it's nearly a normal distribution, and we've used an approximation for sigma, the S. So there's two approximation we've made. Difference in two means. So a motoring organisation wished to determine whether or not the fuel consumptions of two cars models A and B are the same. To do this, 6 cars, each model, were given 10 litres of petrol and driven around a track until they ran out of petrol. The distance travelled in miles by the cars were as follows. You may assume that these are random samples from a normal distribution with common standard deviation 1.5 miles. State a suitable hypothesis, calculate the p-value and state your conclusion when the significant level is 1% and then 5%. So we are given the significance level in this question. So we want to test is the mean A equal to mean B, or are they not equal? So the fuel consumption of car A is normally distributed with 1.5 as a standard deviation, and so is B. They've got different means. We want to check if their means are the same or not. It's two-sided. Therefore, x bar, adding them up and divided by 6, gives us 83.5. Y bar gives us 81.5. So the difference in means would be those. The variance of the difference in means, if we would use our z, so our difference in means minus mu1 minus mu2, we want them to be 0, we want that to be 0 in the test we're doing, and then divided by the square root of the variance. So the variance is 1.5 squared over 6 for both of them, so we add that up and we get 0.75. So we've done the dividing by n in each case. Therefore, our z becomes the difference in mean minus 0 is what we want to prove, if it's equal to or not, divided by the square root of the variance, 0.75, and we get our z being 2.309. Therefore, our p-value, it was two-sided, is one greater than the other, significantly greater, so we want to check. So 2.31, we need the tail of the probability, so 2.31, and we want more than that, so it's 1 minus that, and we double it, so we get 0.021, say. But at the 1% significance level, it's too big, so we would keep H0, so there's be no change in the fuel consumption. But at the 5% level, so this value of this p-value is less than 5%, so we reject H0. At 5% level, there is a change in the fuel consumption. So it makes a difference where you want to pitch your significance level. Another question on difference in means. A scientist wishes to determine whether or not there is a difference in the acidity level of two different liquids. He therefore makes 5 independent measurements of the acidity level of each liquid with the following results. You may assume that these are random samples from a normal distribution with common, so they both got 0.025 as their standard deviation of the original liquids. So we want to state a suitable hypothesis and calculate the p-value and interpret our value in context. He wants to know whether or not it's going to be a two-sided significance test, so either the mu's are equal, the means are equal, or they are not equal. So we need the mean of x bar and the mean of y bar. Then we need the variance of the combination, so we add the two separate variables, variances, and we get dividing by n, of course, each one by its own n, and we get 0.00025. Therefore, our z statistic is the difference in mean minus the difference in what we want to prove, which is 0, divided by the square root of the variances of the combination. So we get z equal to 2.28. Therefore, we want, being as it was two-sided, we want z greater than 2.28. Is that far enough away from 0 that we have made a difference, that there is a difference? Looking 2.28 up in table 3, and we get greater than 2.2, so it's 1 take away what we got on the table, so it's 0.0113, double that, and we get 0.0226. Interpret your value in context. It's greater than 1% but less than 5%, so strong evidence to reject H0. There is a difference in the liquids. Now, we've got 2 examples of small samples with unknown variance. The weight in kilograms of 10 randomly chosen turkeys on a farm were as follows. Assume that these weights can be regarded as a normal sample from a normal distribution. Calculate unbiased estimates of mu and sigma squared. We'll do that first. So, the sum of x is 85.4. The sum of x squared we're going to need for estimate of sigma squared is 734.3, squaring each one and adding them up. Therefore, the expected value of the mean is the mean of the sample, which is 8.54. The unbiased estimator of sigma squared, using that formula, and we get 1 over 9 now, sum of x squared minus sum of x all squared divided by 10, and we get s squared being that. So those are unbiased estimates of mu and sigma squared. Part B. investigate at the 5% significance level a claim by the farmer that the mean weight of turkeys on the farm is 9 kilograms. Use a two-sided test stating your hypothesis. So either the mean weight is equal to 9 or it's not equal to 9. Now, being as we have a small sample and we've got an estimate for the variance, we need to use the T tables, which is table 7. So our T statistics is virtually the same as before, but the numbers in the tables are slightly different. So we want the mean minus the mean of the sample minus the mean that we're proving divided by the square root of the variance over n, being as we're talking about sample mean. Therefore, with T either side, we wanted 5% significant level is two-sided, so we need to split the 5% to each side. So we're working backwards. So we got 2.5% on each side. So our n value would be 0.025 as a percentage there. Our V, now V is the degrees of freedom, or rho, it's the degrees of freedom, and it's n minus 1. Therefore, are we going to use a T distribution, being as the population variance is unknown and the sample is small. So T tables are table 7. Our rho is 9, so we go down to 9 on the left hand side. We want the end bit to be 0.025, i.e. the larger bit to be 0.975. So that's the two lines show us where we need to be. So the critical value now then, plus or minus, would be 2.262. Now that is where we accept or reject H naught. Our T statistic has worked out to be 8.54 for the mean minus the mean that we're trying to prove, divided by the square root of the variance over n, which gives us T being minus 1.975. So is that within the critical region or not? So if we there's our minus 1.975, which is our sample result, and that's the critical value. So we are not within the critical region, so not enough evidence to reject H naught at 5% significance level. So it's virtually the same as before, just different tables, and we are always given the significance level in these questions. One last question. A farmer claims that the mean weight of apples grown in his orchard is 300 grams. His wife claims that the mean weight is less than this. To investigate these two claims, they agreed to weigh a random sample of 12 apples. The result in grams are as follows. You may assume that these weights form a random sample from a normal distribution. So calculate unbiased estimates of the mean and the variance of the weights of the apples grown in the orchard. Then testing at a 5% and then at a 10% level, stating our hypothesis, we will test at 5%, then at 10%. So first of all, unbiased estimate of the mean and the variance, so we need to add them all up and add each square of each one up. So our mean, estimate of the mean is the mean of the sample, is 294. The variance we're going to estimate as S squared, so that comes to 146.18. So we need to test, is our mu 300 grams or is it less than that? So our T, being as it's a small sample and we're estimating our variance, so the T we're using is going to be 294 from the sample minus the 300 that we're testing over S squared over n, divided by the square root of s squared over n as is a sample. And that gives us t being minus 1.72. At a 5%, it's one-sided, so we are looking at 0.95. We don't have to split it. And our degrees of freedom is 11. So table 7, 0.95 as our p, and 11 as our degrees of freedom. We get a critical value of minus 1.796. Therefore, not quite our sample mean, our sample values have given us minus 1.72, so it's not in the critical region, so not enough evidence to say his wife was right. But if we use a 10%, it's one-sided, so we're looking at 0.9 for our p, for our probability, 11 degrees of freedom. Therefore we've got a critical value now of minus 1.363. We are now well within the critical region. Therefore we reject his H0, and his wife was right at the 10% level. There is the mean weight is less than 300 grams. And that's the end of the revision video on hypothesis testing part 1.